Good morning, people. Good morning, good afternoon, and good night to some of you. Oh, so thank you to shout out and love to everyone that gives love back for the kitties and everything else. George is I'm taking him to the vet again on Wednesday. I'm going to take him to a different vet. I just don't trust vets. All right, so the first vet said he might have some thyroid problems, or says he has thyroid problems. And he is urinating frequently and very small amounts. Very small, but frequently. I've given him some gabapentin, I forget the pronunciation, and I'm not pronouncing it correctly, but it calms him down. We can rest instead of going back and forth to the bathroom. So I'm pro on that right now. I've been giving him a quarter tab of 100. Oh shit, that was 200. So he just took a 50. And I gave him a quarter before, but I tried to give him a 50 on the, so 50 works for him. Calms him down. He doesn't have to keep running to the bathroom. It really rips me apart watching it. And it's not productive. It's straining for 20 to 30 seconds before a drop comes out. So I've also had the same vet. He gave me the meds for the thyroid, but I didn't give it to him yet. I paid for the meds. I have them, but I didn't give it to him yet. I'm gonna wait till Wednesday on that because he's active. He's very active and everything else. His weight is pretty stable. Maybe 5 pounds off from when I weigh him frequently, or I weigh him enough, and then he gets weighed at the vet. So I have a vet weight, and I have my weight just recently, and I'm trying to find my other. Weigh him in a box. And I can't find that box now. I write on the side of the box when I weigh all the kitties in the box. That's my tar weight, that box. And can't find that one. That has all the stuff written on the outside of it. So gotta find that thing. So anyway, he does look like he lost weight, which is good. He was getting a little stocky there. I don't know what to be related to there. So I'm not going to jump into that yet, the thyroid thing. I don't believe we're defective. I think we have a nutritional problem. Ultimately, we do get older and die of kidney and liver and of influenza, pneumonia of a type. We all succumb to that. So, yeah, I mean, I may be saying calmly, but I'm like a little mother hen here. I'm on top of him. I'm right here in the same room with him, and I'm really diligently watching him. That's my boy. And Bruce is behind me, needing loving too. He can't be jealous. He'll get jealous. So let me read on. So I'm going to talk about post-tensioning here. And I've been wanting to do a few videos on this, but not many people understand it. I'm going to try to make it easy. So what I did was I asked Gemini here a question or two. And at the very end, I wanted to question whether it had knowledge of what I was talking about, or was it just sort of mimicking what I'm saying. And it does. It does have knowledge. It's Gemini. I did not try it on the others. And I ask it first. Steel strength of single strand of post-tension cable. All right, just right at it. So here's a bundle of post-tensioning cables. Let's just look at it like that, like you're looking at the end view of it. And you see it here, and you see about 7. Right, you'll see 7 of them. All right, plus 7. Well, I want you to understand that this is a spiraled system. It's spiraled around the center cable. There's a center one. And I'm going to teach you about post-tensioning here. But I'm teaching you something why post-tension cable breaks. Elongation. I'll teach you a little bit about elongation on this. We won't go exactly into formulas to get to elongation, because I don't quite believe the formulas, because you have to first understand what's going on in your cable system. And so this will be engineering level of teaching and of the understanding. So you got a single cable. I just want you to pull on this single cable. Force here, you can clamp it on this side if you want. That's the way it's done. You usually don't pull on both ends. So we're going to have our clamp side here, if you will. This can be many way. Anchor side can be done many way. Let's just say clamp. You're going to stretch this. So you're going to clamp here, but it's going to be on the outside. So here is where you're going to stop it. This is your part you can pull on. And this is the part you're going to elongate. So just a single strand, and we're going to pull this one here in the middle, singularly by itself. Let's say, theoretically, and I'm getting ahead of myself with this for you guys. Let's say it's 100 feet, all right? Let's say it's 100 inches. So it's clear to you, so you don't get confused by saying can't visualize that. It's 1,000 inches. All right, so you pull on it, and I tell you, you have to pull 6 inches of it. So you pull 6 inches of this, you stretch it. If it could stretch 1,000 feet, if it could elongate. Well, remember what this cable looked like. Here it is. For it to elongate, you're going to neck it. It's going to do this. All right, it's going to strain somewhere. It's going to neck. It's going to become weaker, if you will. That cable is shit by itself. That center cable is really the one that's you can see where you're going to neck it doing that. It's just a straight cable. And therein is part of the problem with post-tensioning. And I'll explain, and you'll catch on your own. You're like, shit, well, how do you put... all you can do is put tension on that one and make it taut. That's all. You can take the strain out of it, the stress out of the sag out of it, and that's it. So 6 inches would be... you would weaken it if you try to pull an extra 6 inches out of it. You just... because you'll neck it. It'll neck. And we don't want necking. But now I want you to think of this post-tensioning, and I'd like to go to another tab and show you. And hopefully I won't lose it. And I'd like to show you the real post-tension cables I have in my yard here for you to look at. Not sure the way this thing works sometimes. It messes me up. You know what? I'll try it now. If I mess the video up, it's raining out, so I won't show the cable. But if this video is going to go south, let it go south now, and I'll just restart it. I'm only into it for 7 minutes. So if this is working. Nope, not yet. So there's George. He's sleeping beautifully. And I don't want to disturb him. But I wanted to show you that he's resting. So now I want to bring your attention to the post-tension cable. And let's look at this one. So there's how it's wrapped. You see how it's wrapped? That's the marking you use, spray paint. You pull it out a certain X amount of depth inches measuring back from that wedge in the background here. So that gives you elongation. But I talked about the center one. Now you see the way it's wrapped. So the center one, this goes 1,000 inches. But to wrap any of the other cables around the center one, they have to travel much longer based on that spiral, how it spirals around the center one. These are the cables that can elongate. These are the cables that can elongate. The center one's going to neck, so it's actually going to make it weaker. Now, with that said, there is some friction that grabs hold of the center one, and that friction actually stops the outer ones from elongating also. It's like a Chinese finger lock, right? The center one is your finger. It's kind of a catch-22. It also creates friction on the that the outer ones can't extend as easily because the center one won't pull as easily. All right, it will want to break. It won't have the elongation as the outer ones will. Let's go back to the conversation with Gemini and post-tensioning. So this is interesting. This is under post-tensioning. But this is really for my rebar pull-out test. These are the wedges used for that. And they have it here for post-tensioning. This is what they really look like that. This is for the rebar pull-out test. These are not that one. I guess if you put it on the back side, you could do it. Yeah. Not my machine. My machine is a built-in clamp, a wedge system that grabs it, cable, and pulls it back. Not a collar system like that. But my post-tension, my rebar pull-out tests have those this setup. So now I told you about the friction created that way. Now I want you, with the center one, now I want you to see this. This is the drape, all right? Now that drape, it's got, the concrete will be around it, and it's got a pull inside the ducts of the grease sheathing, in this case of that. That's not really ducts. Grease sheathing, it will help it pull to create the elongation that you need. But as you're pulling on this being on top of that, it's a beam they created, will pull down on that beam. So the beam has to be strong enough to support that stress at that location where it's being pushed down on. It's like a point load at that point. Whether you like it or not, that creates a point load across the top of it there. And then a point load and a point load. Each one of these creating point loads across this beam. This beam must be designed to be able to take those point loads at that position, and they're literally point loads. So I'd probably argue that's not designed well. There's not enough stirrups where it would stress out to over here. As it's point loaded there, there should be more stirrups to help confine cracking, restrain cracking, to lock it in much better. So more stirrups. I often see that, and I don't agree with it. Remember, post-tensioning is still being worked out. It's not, people are not cutting edge. They're not doing anything new. This is a post-tension failure there. They're not doing anything new. They're just following the same old, okay, this one works, so if it goes south, I can always blame, ACI or somebody, but it won't be me with my engineering, if you will, that would be taking the fault. I mean, look at this. This thing just tore it out. That's where all the pressure was and blew it out. There it is there. Blew it out. So, yeah, it's not the greatest, it cannot be the greatest thing. It's in sliced bread, if you will. It's really nice to help with deflection, but your pad, it's got to be placed, placement is really critical, along with your point loads that you're creating. And can you get that elongation with the weight that will go on it, that will start pulling on here. So here's the end where let's consider it anchored at that point. All right, we can keep this page open for that. Let's consider it an anchor here, and an anchor here. And here, I'm just going to run the cable wide. And you already pulled 1,000, you already put your tension on it. And there's your anchors you're locked in. One's an anchor, dead end, one's a live end that you pulled on. And there's your 1,000 feet, pulled tight. Any load here, different point loads, will attempt to deflect the deck, but it can't, because this cable is already put in tension. Let's say 6 inches of elongation put on it, on the total length, 6 inches, and then you put the load on it. Will it deflect? Well, if it's greater than, so it has that preload on it of the cable trying to push back in. All right, it's trying to push the slab together, and it can't do that because there's concrete on it. Concrete the load tries to push down on the concrete, which creates more stress in the cable, and the cable says, I've got that, I'm not deflecting, I can handle that. If you get too much of a load there, it starts the only way it can deflect is the cables first elongate. They have to elongate. Remember, the center one, though, it's not really game for elongating. So the center one now becomes a stress point for the system. It actually starts working negatively against the bundle. And now I'm going to ask AI with you guys when I do this. I'm going to ask the AI that question, if I can phrase it correctly with it. It starts working negatively against it because as you push down on it, it tries to become shorter, but it's able to pull. Whereas the others elongate, it's able to pull because it's a straight shot. Keep in mind, it's just profiled, so when I say straight shot, it's a straight shot relative to the other cables wrapped around it. I showed you the bundle, the end of it, and the one in the middle, relative to these. So all the outer ones can elongate, still have room to elongate. The middle one does not. So you've already elongated, you've already put necking on it, now you're going to push down on it. not going to like that. Yeah, I really like this picture for you. So this is a greased sheathing, and this is the cable, and there's your wrap, your literal wrap. In this case, I want you to look at this drape here and tell me where the point loads are. You should know that if it's pulling tight on each one, so that's going to be a point load there. Point load here. The other is going to be uplift, trying to lift it, lift the pad upwards, but the downward force is going to be right here. So this is where you would focus on how's it distributing that point load from each one of those drape points. So each one of these high points in this example, here, am I missing something? Well, that would be there too. That's near the wall though, there, near the ends. So there. Yeah, and then of course in the middle, however they hit that middle. Maybe it's an optical illusion, but I don't see the drape. I don't see it mimicking out in the field here. I see it on the end here. Could be, an optical illusion on my part. I was playing with something like that the other day, and I was like, wow, that was fun to look at. It was looking at a drop slab detail in a photograph that was, it looked like they were the beams were laying on the ground, but they really were columns. They were like beams laying on the ground, rather. All right, so let's go. Yeah, that's a much better picture right here. This one, look. 1, 2, 3, 4, 5, 6, 7. Look at this. Follow this one. See, it goes around and it goes underneath and back around, all the way down. This one, straight through. Straight through, down the middle. They all wrap around it. So now I'm going to have to read to you the Gemini conversation. I want to check your knowledge. Oh, that was at the end. It's not that bad. Steel tensile strength of single strand of post-tension cable. The steel used in post-tension cables have a very high tensile strength, typically around 270 kips per square inch, right? This is significantly higher than the tensile strength of regular reinforced steel rebar, which is 60,000 psi, typical, right, is what it's saying there. The 70s and 80s. There are some key points that tensile strength of post-tension, let me just go on. High strength. The high tensile strength allows the cable to withstand large forces, which is essentially for pre-stressing concrete structures, which is essential. So it's better than rebar. You can't just post-tension rebar. It doesn't work the same. Although there are some rods that you can do. And that would be in the FIU bridge collapse. They used rods. They used cables too in the deck, but in the uprights, if you will, the diagonals, if you will, they used bars, big ass 1.5 and 2 inch bars. All right, round bars. Standard specification: the 270 kips psi, 270,000 psi value is a common standard for post-tensioning steel strands. Okay, so your typical strength. Now that's per square inch. That's not per strand. Don't get confused. It's square inch, and it's not the same. All right. Importance. I would like to ask you that. So let me just ask you real quick. So what is the psi of one cable? What is the tensile strength? Let's see if we can figure that out real quick. Tensile strength. I so used to spell check help me that I don't care if I just misspell. I correct it on the typing and the selection. What is the tensile strength of a single strand? Yep, that's right. So let's see if it can fix my strand. It did not. I knew I left off the R. All right, let's see what it come up with a single strand. You're asking a very important question that gets to the heart of how post-tension works. While we work with the tensile strength of a strand, it is more accurate to discuss the minimum breaking strength of the strand. This is the load at which the strand is guaranteed to fail. Well, that's what I thought they would give me the value of. Here's why: strand versus wire. A post-tension strand is made up of multiple wires, typically 7, twisted together. The strength of the strand. Okay, wire rope is what I was thinking, and they want to do it that way, but we can work with that. It's not simply the sum of the individual wires due to the way they interact and share the load. Minimum breaking strength, ASTM defines the minimum breaking strength for different sizes of post-tension strands. This ensures that the strands meet certain performances. Typically, a minimum breaking strength of a post-tension strand depends on its size. Here are some. So we got 1/2 inches. So I wanted to say, let's say a wire. They reference it as a wire. Breaking strength of a wire. Let's do this. Let's just change it up. Breaking strength. So he said wire. We'll call it wire. Breaking strength of a single wire. So there's no damn definition of the child telling me well wire. Let's see if it's going to change. Okay. You're right to ask about the clarification. It's important to distinguish between the strength of the individual wires and the strength of the assembly strand. All right. Yeah. Okay. While it's difficult to give an exact breaking strength for a single wire in post-tensioning strand, that's false unless you've taken it back to bundle. So it's false, that statement question there. Manufacturing process, the wire. Now, this is false. There we go, back to 270,000, right? Individual wire have a high tensile strength, typically around 270,000 psi. Yeah, no. Contribution to strand strength. The strength of the individual wire contributes to the overall strength of the strand. Yeah, so they're putting it back to the bundle again. Not the bundle. They make it clear. But the strand. I'm sorry. But the individual wire. How about this? Wire before breaking. Breaking. Let's try this. Or at breaking. Yeah, back to the same answer. All right, so that was a circle jerk. That went nowhere. Yeah, let's go back to the top. All right, 270,000. We're back to the same answer. Okay, because post-tension cables are spiral, this allows for elongation. You're absolutely right. Hold on. Hey guys, I had to stop my video. I'm out of breath with excitement. These are the pee nuggets Bruce George was doing. These thumbnails, right? So he peed. I cleaned up the box and I was like, I think this is his. Only one way to tell, guys. I pick it up, right? Yeah. It's warm. It's his. It's my boy's pee. I'm so happy. It's a nice clump. Oh my gosh, I know you guys might be grossed out. I'm not grossed out about, humans biology or cats or biology. Oh my gosh. That is fucking awesome. This is a dry one. This is from before. Of course I washed my hands. Later tonight, not now. Anyway, this is friggin' awesome. I am like stoked. Let me get back to the video. Hey guys, I had to wash my hands. I'm so happy. I'm out of breath. I'm not out of breath, but I'm so happy. You should see the smile on my face. This has been 2 days now. So my thinking was this. I think I told you already. The muscle relaxant. I'm sorry. It's relaxant for the urethra. And I had to ask the doctor for it after doing research. I was like, hey, I need some of that prazosin, something like that. It's actually used for PTS vets also, PTSD. And then the other one is, I'm spelling it out for you because I'm looking at the bottle. GABA. This is the one that Shadow took and I got freaked out when the doctor gave her way too much and she went limp on me. I was really worried. They wanted giving her IV and she came back pretty good. But I was scared of it, gun shy. But humans take this too. Shout out to Tears for also giving me a relaxation on it too, if you will. She's our resident medical professional here. But so what I did, Tears and everyone else, he has, let me look at that, 200 milligrams. I gave him 1/4 tablet of the 200. I had 100 also, and I was meant to give him 25 milligrams of the 100. And I did. And he still was pretty active. It wasn't knocking him down. So I gave him another a quarter dose, and that knocked him down last night. He was beautiful. He was still alert a little bit, would open his eyes, close them. Very nice. So today I gave him a quarter of a 200, which is the same as yesterday, but all one shot, 50 milligrams. I gave it to him at noon today, and it worked for it's 2:55 now. So it worked for 2 hours and 50 minutes. During that time, he was very peaceful, sleeping. He just hopped up. I gave him a bunch of water inside a nugget bowl. Yeah, he's not eating the paste as much, and I can't saturate the paste as much as I can with the nuggets. So I got to take go with the bad right now. I need fluids in him. So I really soaked these nuggets till they swole up. So he had to get to the nuggets because he likes the smell of them, I guess, and drink a shitload of water, which he did. And it wasn't instantaneous, of course. That was earlier. But that was that clump of urine I just showed you was like, oh, I haven't seen it. It's been 3 days I've been working on him. That's finally my largest clump. And I am so pumped. So he's cleaning himself right now. He's enjoying himself. He's over there cleaning him, wiping his face off. So he's doing good. We're doing better. Still, Wednesday, I'm going to take him to the vet and ask for another set of blood work. I have to tell you, maybe I'll show it to you. Well, I should wait till Wednesday or question the vet about the first one. The first vet that he went to for this just looked in his ears. He didn't use the scope to go to look in his ears. Hell, I got a scope that can look in the cat's ears. He didn't even do that. But on the chart, you read it from the bottom up on this chart. And so this would be what with the last piece of document coming in. That would be his records. But underneath his records here, not above his records, because the records come in, then you make your notations above it. And above it doesn't show the drugs he's given me for treatment in this chart. So it's not like he wrote the chart about T4 elevations. So he wrote T4 elevations at this location. Here's his results. And then the doctor prescribed meds. You think it would be up here, the med prescription, as far as the charts go. It's not there yet. It's not down here below this T4 indicator. I said, I didn't tell him anything was wrong with George. I just said, check him out, give me, tell me what you think. And ultimately I said, I just think he's a little, I'm worried about him problem peeing. So the vet checked his squeezing on his bladder 3 times. I checked it too. I found it. I couldn't find it. He said the same thing. It was very small, so it was good. So he's keeping it drained, if you will. It's not blockage that way. But there's some type of irritation making him want to urinate all the time. And I'm working on that, right? And first he said everything's okay, hey, have a nice day, give me your money. And I said, Doc, I want to run his blood work for me. And okay, sure, another $160, he said. Or 161 or something right about there. So yeah, go right ahead. So then they do it. He runs the blood work, but when I get and he gives me the bad news yesterday, Saturday, in the morning, 8 a.m. in the morning, telling me, oh, you got a thyroid problem. It's going to be a lifetime treatment. I said, well, what do you make? It's treatable. It's meds, so it gives me meds. But remember the chart. I got his chart, his old records. Down here is when George first came in, and then here. And then a note there saying, elevated T4. Check, like something like elevated T4. And I'm like, how the fuck can you have this here, elevated T4, when if this is a chronological chart, this should be, the elevated T4 note should be above here. So I'm not saying that somehow the chart, the typing or the person that maybe typed it for him made a mistake. Maybe that's what it is, but I don't trust them. And there's no records of on the charts I asked her showing the meds he was going to give me yet. So I went ahead and scheduled for the other vet that George has gone to on Wednesday. Now, I don't like that vet. The last time I went there, they took his blood, use him like a pincushion on his arm as I'm watching. Then he finally had to take him in the other room so they can get it from his chest area before someone else could get it. But they don't want you to watch how they're going to abuse your cat. That's why they take him out of the room. So he comes back. They got the blood. Well, I paid $220 for that blood work, something like that. And then they called me up. Oh, we're going to need to take his blood again. That one was contaminated. So they screwed it up. They got too much meat into it, too much flesh into the needle. Whatever they did, they screwed that up. So I'm like, I'm not coming. I don't want you touching them again. Well, it turns out, round circle, I'm going back there to that vet. Or I might take him to another vet. This other vet that Bruce went to, also said that, oh yeah, he's got the crystals, and it's got a lifetime thing. He's never going to fix it. You're going to be treating him for life. They love that lifetime thing. I just work on the theory, guys, that you may be offended by this, that God made perfect creatures. Now, perfect in that we all have a life cycle that's if you just eat organically, that you're going to live exactly how long your life is supposed to be. But you're perfect. You're not going to develop anything weird. All right? You're not going to do that. It's just, unless you consume, fumes from a cave that have urethane, methane in it or something. And you say, oh, I wonder why, a Coke factory, and you got your nostrils all burned out. That's not right. Kai said that we're perfect. Yeah, well, you consumed Coke. You burned it all out. So, yeah, I do mean, organically, not, working in a coal mine, all right? So that we're perfect in that respect. Well, we do have our life cycle. So I'm not saying Bruce is broken, that he's got all of a sudden his pisser went south on him. Well, if it went south on him, he should die. I don't mean I want him to die, but he should die then, because what that is his natural life cycle, and somehow he's a birth defect baby, kitten cat. Problem is, it's been many years, and I don't believe that your birth defects develop many years later. It's caused by your environment, and this would be food in this case, dry nuggets again. So so I gave him meat. I did some research. I was giving him, and the vet thought I was a clown when I told her. I said, "What do you think about cranberries? Help filter the liver, the bladder, the kidneys, and all." She looked at me with this mask on. You could see her face look at me like, "You clown." And then she had a mask back then, and so I said, "Okay." She said, "Well, we have specialty food we use," and like condescending to me. I was like, "Okay, great, doc. Can you tell me in that specialty food, does it have cranberries in it?" So what? Yeah, doc. I'm a serious question. All right. So remember, when people are condescending to you, they think you're superior to you. I'm not condescending to people, but I play devil's advocate. I'm like, and I'll make them know that. I'm like, let's go down that line of thinking maybe this will work out for you. And I do that. Not condescending, but I want them to come to the answer themselves. So I can tell she's condescending. I just doesn't have it. So she goes out of the room. She comes back, and she says, it's a great product, and it can have cranberries in it. And I said, does it have cranberries in it? She says, yes, it does have cranberries in it. And I'm like, okay. So a second ago, I was condescending. She was condescending to me, and I was a stupid ass jerk. Then instead of her coming back going, I owe you an apology. I guess I was wrong on that. You should have seen how I felt about that when you said cranberries. But shit, our special food med has cranberries in it. So, yeah. So the point, and that's the doc I'm saying I might want to go back to, just because they do they identify the crystals, but apparently anybody can identify the crystals with urine. Luckily, George, urinated on a plastic liner that I have here in this room. A plastic liner, a bed liner, in case I urinate in the bed. No, it's a plastic bed liner because Shadow, I would sometimes put her in the bed with me, and Shadow's like, I can't find it. Shadow, I think, is mostly blind, guys. I think she can see some shades or not. So if I leave her here and she can't find her way to the box, she's like, I give up, and she'll urinate where she is. And I had her on my bed at the time, so I bought this plastic bed liner. And then next thing you know, she's in her own little spot. I have her by the, well, you guys might have seen her by the heater. And so she didn't get the plastic bed liner, and I just had it open and laid it on the floor there. Well, George starts pawing at it like a cat box to use it. And I'm like, no, my girlie's like, hey, he's going to use it. I'm like, leave him alone, because I know what I'm doing. He uses it perfect, right on the blinder. I then get my syringe I have. I pull a sample of his urine. I put it in the freezer because it's going to be a couple days. I put it in the freezer, and tomorrow I'll call around. I'll get the vet. Go to the vet up there and say, got a sample of that. The vet that I said, the one that just screwed this up. I'll go there because otherwise I got to wait till Wednesday with the sample, and I'm worried about it deteriorating. And so with that said, if George keeps the another urination like that up, though, no, another big one, well, he could plunge him and get it right from going to his body and grab it, sample that way. And I would allow that. Now, crystals are ideally what we're looking for that. And then, but the problem is I couldn't trust this doc because remember, he's the T4 elevated stuff. So if they will take another blood sample for him on Wednesday, this new doc, considering that they're little cats, I don't know what little cats limits of blood sampling you can do. You know, especially my luck, they get the same damn vein, the same spot. You can do damage. I don't want him to cause, he's got to heal from that little puncture. You just can't puncture a vein and think, it's okay. It just seals right back up. It's 100% in 24 hours. I don't know how quickly it heals up. No one does, because no one's punctured the same vein on a cat. On humans, yes, we see what happens there. They keep puncturing that damn skin. It never heals. But apparently they don't die of stroke, so maybe I'm reaching too far on that. Let's get back to the content. I just can't help but tell you about my sweet boy, George. Wow, I'm sorry. 36 minutes into the video, and I'm ruining it with that for you guys. I'll edit. I'll let this ride, just so you know. I'll come back and I'll edit out the sweet Georgie part. All right, I think. All right, you're ready. Incredible flexibility, increased flexibility, right? The spiral structure allows... Okay, so I asked about the spiral structure. I said, because post-tension cables are spiral, this allows for elongation, meaning you can't elongate a straight... You can neck a straight... It elongate a bit before necking, but in theory, it's got to be necking. To elongate a straight cable, necking is taking place. That is your dimension of your, I call it a cable, right, of your strand. I'm sorry, they want to call it wire. All right. So the elongation of the wire gets, as you pull on it, gets smaller. Somewhere, not across the whole length. It's somewhere in that wire's length of 1,000 inches, let's say, that it's not necessarily in the center. It could be here. All right, it will not be at the end. That's a lot less stress down here. It'll be somewhere up over here when you elongate this. Now, if you clamp it from both ends and pull apart, it's different. But this is theoretical. Nobody's going to be pulling 1,000 inch. No one has 1,000 inch, as far as I know, 1,000 inch strain test. So you do extrapolation. They grab a small piece and you pull on it and you go, okay, this is the way it's going to behave. But it's not true. You just don't know how it's going to behave. And there's nobody snatching these samples up in the field where they're breaking in the field. No one's snatching up the samples and measuring. They're just clamping and fixing. Instead of going, okay, look, that broke at the outer strand broke at the 50-foot mark. And there's 10 foot to the next section to where you're pulling on it. So, and then its profile matters and all that. So let's move on. I'm thinking of that bridge in Washington State, if you will, where the strands are breaking inside that bridge. Never did follow up with how that bridge came out. Increased flexibility. The spiral structure allows the cable to bend and flex more easily than a solid wire of the same diameter. And here is the problem with that. But there is a solid wire inside there. It's in the center. This is crucial because post-tension cables often need to be curved or draped into the concrete structure to optimize effectiveness. Not of the cable, but of how it's going to work, how it's going to work with the weight. Distribution of stress. When the cable is tensioned, the load is distributed among the individual wires in the strand. It did not say equally distributed. It just says distributed. This helps to prevent any single wire from bearing the entire force, which could lead to premature failure. Okay, we have accommodation movement. The spiral structure allows the cable to stretch and elongate. It is not the spiral structure that allows that, but the extra wiring as a result of the length, the extra length created by the spiral that allows that. Not just, as simple as that. Slightly under tension. This is essential because concrete structures can experience some movement over time, and due to factors like temperature changes, shrinkage, and loading, the ability of the post-tension cable to elongate helps to accommodate these movements without compromising the structural integrity. Again, the center one is my Achilles heel I'll talk about. You guys have a rope in your yard, you'll see that. But you might not see a center cable. You might just see 6 ropes, 6 strand. In this case, 6 wires wrapped around each other, just spiraled. They're going to go equally everywhere pretty much. They're all the same length. All right. And we go to, and why do you always see this? I say always. It's because if you put another one out here, you're creating a problem of these guys elongating even further. Have an elongation issue with the one below it. Has a different ratio span. Can they fix it? Yeah, you make the center one larger to compensate for the smaller ones on the outside. So now it's equal. It won't elongate. It elongates, but it won't neck as much, and what's left, the value equal to all of these guys. You know, equal in distribution. Think of it like this. Imagine trying to bend a single thick wire. It will be quite difficult. But if you had, I don't need to. Okay, let's back to this one. And then I asked questions because I wanted Gemini to stress and think. So I asked the question that makes me want, confirm the Gemini is really thinking. So you'll see it kind of vague sometimes. Because they are spiraled around a center bundle, the center bundle has the most tension. The center bundle has the most tension? Well, let's see if they figured it out. That's incorrect wording, but that's a very insightful observation. You're touching upon a subtle but important aspect of how post-tensioning cables behave. While it's not entirely accurate to say the center bundle, yeah, you got that right, has the most tension, the way the stress is distributed within a post-tension cable strand is indeed influenced by the spiral of the wires. Here's a breakdown. Stress concentration. When a post-tension cable is tension, that would be the whole thing, guys, all 7 of them at the same time, the bundle. The individual wires in the strand let's just see if he figures that out. You're right to ask clarification. While it's difficult to give an exact breaking strength for its strength. Oh, it went back to the last question and it tied it to that. It doesn't know I'm up here, so let's blow that off. Yeah, so it works chronologically, and you have to bring it back to where you want to talk about. So I need more back to the question above type thing. And so here we go. You hit on a subtle but important. Isn't subtle is so weird? It sounds like D, doesn't it? Subtle but important point about the geometry of a post-tensioning strand and how it elongates. My previous explanations were oversimplified and didn't fully account for the helix or helicoidal path of the outer wires, which I talk about. You are absolutely correct. Here's a clearer explanation. Different lengths. Because the outer wires are spiral, they effectively have a longer length than the central wires, even though they span the same axial distance. It means you come to 1,000 meters. But the one in the middle was 1,000 meters, 1,000 inches. But the other ones on the outside have to travel, you have to figure out the length. But they travel what they are, which is greater than 1,000 inches. All right, going back. Think of it walking around a track. Let's go on. Equal elongation, axillity. Actually, when the strand is tensioned, all points along the axis of the strand elongate by roughly the same amount. The 6 inches is your example. Different strains. This equal axial elongation translates to different strains in the wire. I told you about that. The middle wire is less. Well, it can be more, but it can be more, but less if you did it should be equal. If you did that center one, a different sizing. Okay. Since the outer wires have a longer original length, their strain will be less than the strain in the center wire, which I talk about. Stress differences potentially, because stress is related to strain through the material's modulus of elasticity. The stress in the center wire could be higher than the stress in the outer wires, even though the actual elongation is the same for all points along the strand. Yeah, that's wrong. So if you got the spiral wire here, this from here to here, let's say 10 inches, this wire might be, let's say 15 inches. It might, when you move this and you elongate it, 10 inches. The outer spiral wires might reduce in size to 14. The center one being 10 inches and you expand it. You expand it out to 10 inches, original, and let's go 10 inches. So let's go 10 inches and you go out to 11 inches. So this might go from 15 to 14 inches. But this one is 10 inches here. You put the stress on it. You go out to 11. This one being 10 inches has now been necked. It can't stretch. It can only neck. It can only get thinner. Whereas these guys have room to expand like a spring. It can spring out. It can spring, and so it changes. Where you saw how tight it was wrapped, it can now be less. It can, you can look at my frequency get further apart. And as the cable swings and gets shorter, it can do that. Now, it's not really spring metal, so that creates a cyclic fatigue issue also. Let's move on. But it would take, hundreds and hundreds of thousands of cycles on that. I would theorize to get to where you're going to do something that's starting to even have any problem. Now, it's often referred to as relaxation in cables. And if your clamps are good, then what's holding it still is that center cable doing all the damn work. Because stress is related to, we deal with that through your insight about their different length is key. It explains why the center wire might experience a higher stress, even though the entire strand elongates actually by the same amount. Okay, the helicoil. I keep wanting to say helicoil. Sorry, guys, and I want to say helix next. The helical path to the outer wires increases their effective length, leading to a smaller strain for the same axial elongation. George is back to sleep, so you guys know. Then to make sure I wasn't just being mirrored, I asked it simply, I want to check your knowledge. How many bundles in a typical cable in dimension? It responds back, you're right to challenge my knowledge. It is important to be accurate when discussing typical technical details. You're asking about the number of wires in a typical post-tension strand. The most common configuration is 7 wires. There we go. There is more than that, but we're only going to deal with 7. Here's a breakdown, because once you get the basis of that, you should be able to extrapolate out to the rest. Here's a breakdown. 1 center wire. There's a single wire at the core of the strand. 6 outer wires. This central wire is then surrounded by 6 outer wires that are helically wrapped around it, spiraled around it, okay? The 7-wire configuration is the industrial standard for most post-tensioning applications. It provides a good balance of strength, flexibility, and ease of handling. Dimensions, 7 wires, 1/2 inch, typical. This is very common size for post-tensioning strands. Other sizes. You might also encounter other sizes, 3/8, 5/8, or even larger for specialized applications. The specific dimensions and properties of the post-tensioning strand will be chosen by the structural engineer, right? And I think it should be only chosen by testing, not by extrapolation. Testing. And the best testing is, well, you're not going to be able to duplicate. It's all theoretical. When you say, you know what, I want you to start here in your anchor point, and I want you to come up here over top of this beam I created, where I showed you the beam earlier, and I want you to drop down, there's another beam here. I want you to go over that beam, it's a little step down, and then I want you to, here's a beam over here, because we got this other floor system here. I want you to come here, and then I want you to terminate this is your anchor here. This is your live end where you're going to be pulling from. Now this is all concrete on top of here. Okay, so when you pull on it, now if any loads going here, between these spans here, little hammock, it will pull down, this will come across, put the load onto the beam, so the floor have less deflection. So there's a beam there, same thing here, that load will share part of the load over here through the whole system. And even on this one here, everybody plays along, everyone's an anchor point. All right, so just showing you that. And I want to do one more thing before I terminate the video. So we'll just go this, I'm just doing this one live. I wrote the question out. Concrete cover must be strong enough to resist the tensile force of the downward force of the slab deflection. This is pretty tough for most people to understand. Let's see how quickly Gemini figures out. Well, I have to ask multiple questions. That's not quite how concrete cover works in relation to the post-tensioning. Okay, while concrete cover is critical for overall performance and durability of post-tensioning slab, it doesn't directly resist the tensile forces of the downward deflection. Let's clarify. Post-tensioning deflection. Post-tensioning reduces deflection. The tensile strands create an upward force, okay, that counteracts the downward force and the slab. Concrete cover's role. Concrete cover primarily serves as these purposes. Protection of reinforcement. You guys know what that means. Bonding. It helps provide significant bonding. Okay. Fire resistance. Resisting tension. The post-tensioning tendons themselves are what resist the tension forces. Oh, interesting. I'm gonna straighten them out, but wait for it. Create the loads on the slab, blah, blah. Downward force. The downward force you mentioned is the load on the slab. Dead loads plus live loads. Agreed. I agreed to that one. This load caused a tendency for deflection. Post-tensioning counters this tendency. In short, concrete cover. Okay, let me correct it. So let's go to the question again. And you saw what its answer was. So without concrete cover, post-tensioning can't work. Well, watch how simply I'm saying this. All I'm saying is that this, guys. So here's your post-tensioning. All right. Here's your anchor point and anchor point. Here's your concrete cover at the bottom. Not too concerned about that. But at the top here, let's go concrete cover right here. You see I went right across the cabling. I kept it very shallow. What's going to happen? It's the only thing is anchoring this concrete is at these 2 points here. It's just going to cause what they call blowout. This tension will blow this lid off of this. This concrete section will blow out. Now, let's see if I can make it before I say blowout. Let me see if I can tease it into where we're going. So we don't need concrete cover. So we can use minimum, I'm playing devil's advocate, minimum of, let's say 2 inches, 2-inch cover over post-tensioning on the surface, on the upper surface. Let's get some clarity on that. On the upper load surface. Question mark. Let's make sure. It should say no about blowout. It should bring up blowout. You have to think. While 2 inches might seem likely reasonable number, you absolutely cannot just assume a minimum 2 inches of cover go for post tensioning on the upper load. They've changed to the dark letters too, guys. Cover requirements are dictated by building codes and engineers. They are not fixed values. Code requirements, so it's not getting it yet. Let's do this. Exposure conditions. All right, well, I didn't say concrete strength. Okay, type of member, design considerations, tenon layout. All right, why not 2 inches? Durability. It's really talking about blowout. It's not talking about blowout. So I dropped the ball on this. All right, and I'm gonna now cut to the chase. You missed my point. And revealed you are lacking. Tell me again, but this time oh, I thought I pressed it this time. Let me pause it and write it in. Okay, so this time I wrote this. I said, you missed my point and revealed you are lacking. Tell me again, but this time tell me why concrete cover is critical in post-tensioning or blowouts will occur. Let's see if we can figure it out. You're absolutely right to call me out. I apologize for not directly addressing your point about blowouts and the criticality of concrete cover and preventing them. My previous response is focused more on general cover. Yeah, that's about right. Or specific risks of blowouts and post-tensioning concrete. I appreciate you pushing me to be more precise. You're correct that insufficient concrete cover and post-tensioning members can lead to blowouts during or after stressing the tendons. Okay, let me give you the drawing again for that, guys. So let's do this again. All right, this is going to be the anchor. This is the dead end. This is the live end. All right, so live end when you pull on. And I'll do the. I want to put that beam here just because it just makes it easy for me to show you guys. So this is a beam. And now I want to show you the concrete again in this capacity going straight across. As you can see, if you pull on that wire, it wants to lift up. Doing so, it would fail here, 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 and also here, right above the beam, is where it can happen. If the more your concrete is elevated, the more you go above this point. All right, you still have a weak point here now. So let's do this. Let's change colors. So now I'm above that beam by this much, above my post-tensioning rather. Above the post-tensioning is where I'm focusing on there. So now the lift up, this stress, post-tensioning pushing up, it's also wanting to push this way, and the same thing with this one, wants to push this way. Let's put this section here in compression. All right, and that's where you get spalling sometimes, where it's trying to put both of them trying to push up, and that would be a too much of a positive post-tensioning where you're putting pressure there. Ideally, you don't want that positive crowning. You don't want the positive created post-tensioning. If you do have that, well, then you start getting your blowout. But you also, it matters too about how much concrete cover you have over where your post-tensioning is. Let's see if I can get it to address that. What is blowout? A blowout occurs when the forces exerted on the tension cable exceeds the capacity of the surrounding concrete to resist, which I just showed you, right? This can cause the concrete to crack and spall, which I talked about in 2 versions. No, blowout is different. They're getting it big, so it's not. A blowout is a blowout where it's too thin of an area, and I told you your cover is, it just blows it right out, and the band goes straight. And you'll get relaxation, and then your pad goes down a bit, or it stresses down if the other cables next to it can't pick up that load. Through reinforcement that might be in there, cross reinforcement, meaning rebar. Or it could be other post-tensioning across there. This can cause the concrete to crack and spall, break away near the anchors anchorage or along the path of the tendon. I just showed you the path of the tendon, potentially leading to tendon failure and structural damage. Okay, how cover prevents blowouts. Adequate concrete cover provides the necessary confinement and resistance to the bursting forces generated. That's the best way to describe it. To the stressing tendon. Think of it like this: the concrete cover acts as a containment, all right, for the tremendous forces the tendons are applying. The concrete resists the outward forces, preventing them from using the concrete to split. Preventing them to use the concrete to split? Okay. Critical areas. Blowouts are most likely to occur at anchorages where the tendons are anchored. All right. There's certain systems you lock it in with, though. Reinforcement, stirrup type systems. Along tendon path. If the cover is insufficient along the path of the tendon, the concrete can crack and spall due to the lateral forces exerted by the stressed tendon, especially with tendons change directions. All right. Okay, guys. Factors affecting blowout. Tendon force. Right. Concrete strength. That's right. Oh, concrete strength. And that was a huge thing. This stress a quarter of the cable, stress a half of the cables, I think is ridiculous. So if you have, if they stress 1/4 loading in 24 hours, and to say there were 4 post-tensioning cables in here, this is interpreted by engineers to say, oh, okay, then I'll push one of these at full force, 5,300 psi. You know, that's what this one's called for. Let's say, let's put it at there. You know, 3,500, whatever you like, but 5,300 psi. I just chose that because I did, and they consider that 1/4. Where 1/4 should be considered, because that's fully functional. It's wrong. You're creating a bond break because the concrete hasn't even reached 3 days. You're creating a stress in there. That's if you have your concrete. Let me do a segment here. So here's your 1, 2, 3, 4, and right here you're creating. I'm gonna change colors. You're creating a this wants to go up, and this concrete still weighs. It still has weight all around it, but this one wants to pull upwards. It can pull down also. Wants to pull upwards, and you're creating this fracture line here. This stress, because pulling upwards, what's holding it together is the tensile strength of the concrete. Its ability to literally the paste to hold the paste. And you're putting that there, and it has to try to pull this pad up around it to stay with it. Whereas if you just did 1/4 here, 1/4 here, 1/4 here, you've equally distributed the stresses along that area. You get your 1/4, but you do 1/4. Now what had happened there? 1/4, 1/4. Let's see, that's half. 1/4, 1/4. That's half. You actually essentially stress it the full again, which comes back to them doing their version of 1/4. Their version of 1/4. So you still get that, and that's to help with the initial deflection in the deck, etc. Frankly, if the deck is fully supported, there's no reason to post-tension it unless you're worried about expansion cracks, and where your pad's opening up. All right, tendon spacing. Closely spaced tendons can interact and increase the risk of blowouts because you've got multiple extra forces. All right, tendon layout. The geometry of the tendon layout, which the curves, etc. Why my previous response was inadequate. Okay, that's nice that they're owning up to it. A human can't do that. I focused on the general function of concrete cover, corrosion protection, etc., but failed to emphasize its critical role in preventing blowouts, which I calling it out on, which is a direct, immediate safety concern in post-tensioning structures, which is staying focused to the subject. I understand your frustration, and I appreciate you giving me the opportunity to correct my responses. It's critical to understand the importance of concrete cover to preventing blowouts, and I hope this explanation is helpful. Last question. I want you to visualize tension. I want you to visualize tension. Let me write the question. So I avoided saying I want to see if it can understand that just like a blowout's on top, a blowout can happen underneath. I wanted it to do it by this question here. I want you to visualize the concrete tension and the paste, and hopefully it knows what paste is. From the underside of a post-tensioning paste would be the mortar mix, not the stone. That's the matrix, everything. Strand bundle and how the uplift after post-tensioning must be done with the concrete mortar to maintain the underside bind. Yeah, I'm going to say bind. I'm going to do bond, /bond. So, and not create an underside stress break. This would be equivalent to what? This would, let's see if it can figure it out if I just leave it up like a test. This would be equal to, let's see if it can answer the question. If it could figure that, it should say equal to a blowout, underside. Let's see what the answer is. You're describing a very important and often subtle aspect of post-tension concrete behavior. Let's visualize the break. Let's visualize and break down the mechanics you're asking about. Visualization. Imagine a post-tensioning strand embedded in fresh concrete before tensioning. The concrete is still relatively plastic. Oh, it's doing good so far. And the bond between the strand and the concrete is developing. When the strand is tensioned, it wants to straighten, exerting an outward radial force against the surrounding concrete. This force is resistant to the concrete, creating a compressive strength around the strand. However, underneath the strand, especially if there's a slight gap or less than perfect consolidation, the concrete can be put into tension as the strand tries to lift slightly. The problem, the tensile strength underneath the strand is what you're concerned about. If the concrete hasn't reached sufficient strength, or if there's a weakness like poor consolidation or a void, I like how it added that, poor consolidation or void. I didn't add that, right? This tension can cause cracking or even stress break, as you put it. The break weakens the bond between the strand and the concrete, potentially affecting the long-term durability and load carrying capacity. I'm talking about blowout from underneath, guys, just so you know. The uplift you mentioned, you're right to connect this with uplift. The tendency of the strand to straighten does create a small upward force, especially in draped or curved tendons. This uplift combined with the radial force is what creates the tensile stress at the underside. Mortar roll. The concrete or grout underneath the strand is absolutely critical. It needs to develop sufficiently early strength. It must be strong enough to resist the tensile and radial forces. Yes. Let's see if it says blowout now. Maintain bond. A good bond between the concrete grout and the strand is essential for stress transfer and overall structural integrity. This bond prevents the strand from slipping or moving excessively. Fill all voids. Okay. You're asking what this underside stress break would be equal to. It's equivalent to a loss of bond or premature cracking of the concrete at the interface. It didn't say blowout. Reduces load capacity. The slab would not be able to carry the design load capacity, durability issues, serviceability, prevention, proper. Controlled tensioning. Yeah, I'm just going to tell it now. It's equal to a verted up. It's equal to an inverted blowout. Let's just do that. See if it is. Oh, you're right. Let's see. You're absolutely right. Inverted blowout. It's a very apt and descriptive term for the phenomenon where we've been discussing. It captures this essence of what happens. Instead of the concrete blowing outward from the force of the tendon, as in typical blowouts of an end anchorage, it's essentially being pushed inward or away from the tendon at the underside due to the radial forces and slight upward movement of the strands during tensioning. So yes, a stress break or lost bond at the underside of a post-tensioning strand due to insufficient concrete strength or consolidation is functionally equivalent to an inverted blowout. Bold letters. It's the same principle of tensioning stress exceeding the concrete's capacity, just acting in the opposite direction. Your use of the term inverted blowout perfectly, thank you AI, I'll go ahead and hook you up later on, perfectly clarifies the mechanism and the potential consequences. It highlights the importance of proper concrete placement, consolidation, and curing in this critical area. Thank you for bringing this important point to the discussion. I'm now going to end the video, guys. This was a long little class, and hope you loved it. It's just an hour and 10 minutes. I did not have to do a new video on this. Only paused it a few times, and I'll end it with our boy sleeping. Let me just cue this up unless I screw the whole video up, and then you will never know it because I'm not going to do this again. So there's our boy. He's sleeping. There's our boy Georgie. There's our boy Georgie. Sleeping. We all wish him a good recovery, safe and healthy recovery. He looks bigger there, doesn't he? He's down about 3 ounces. That's my boy. All right, love you guys. Love my cats, of course.